Hi guys, it's Andre from High Performance Academy. Welcome along to this webinar where we're going to be discussing the subject of measuring exhaust gas temperature or EGT in a common rail diesel engine. Now first of all, we're going to start with why we would want to monitor our exhaust gas temperature. And really it's not the exhaust gas temperature specifically that we're interested in. What we're trying to do is really get a bit of a feel for what's happening inside the combustion chamber. What we're really interested in is the combustion chamber temperature. Unfortunately, unless we're working for a very well-funded laboratory, someone doing really in-depth research on diesel engine performance, it's very difficult to directly measure the combustion chamber temperature. Very difficult and also very expensive. So what we're doing is we are measuring the exhaust gas temperature, which understandably is a byproduct of the combustion process. So we're not seeing firsthand what's actually happening inside the cylinder. Instead, we're trying to infer that by looking at what's coming out the exhaust ports. And this, in the diesel tuning world, is a fairly common metric to keep track of the health of the diesel engine and keep an eye on the condition of the tune. So that's why it's common, and that's why we're going to be talking about it today. As usual with all of our webinars, we will be having a question and answer session at the end of the lesson. So if you do have anything that crops up that you'd like me to discuss, anything that I talk about that you'd like me to go into more detail on, please ask those in the comments and the guys will transfer those through to me. Okay, so before we move into how the exhaust gas temperature is relevant to us, and we will be having a bit of a demonstration here on our mainline dyno as well, before we move into that, what we want to do is understand a little bit about the diesel combustion process. And really what I'm going to be talking about here is a comparison between the diesel combustion process and the gasoline combustion process. What we find is that most tuners that are now trying to transition into diesel tuning have grown up and sort of cut their teeth in the gasoline tuning world. And when it comes to diesel tuning, it's almost a polar opposite. The way the engine responds, particularly to fuel delivery, is dramatically different. And one of the key points here is that in a gasoline engine, we tend to see under high load, the exhaust gas temperature will run within a relatively narrow range. And the reason for this is that the gasoline engine also runs across a relatively narrow range of air-fuel ratios. So for example, I'll talk in lambda here just to remove the confusion that may come with different stoichiometric air-fuel ratios. But for a naturally aspirated gasoline engine, we may be expecting to run somewhere in the region of maybe 12.5 to 1, sorry, 0.85 through to maybe 0.92, maybe even 0.95 lambda, somewhere in that range. If we're talking about a turbocharged gasoline engine, we're likely to be running somewhere in the region of maybe 0.75 through to 0.85. So relatively narrow range, where on the diesel engine, we're running across an incredibly wide range of air-fuel ratios, and we're always operating on the lean side of stoichiometrics. So that's really important to understand. The issue here, or the consideration here with the diesel engine, is that we don't throttle the airflow or control the airflow into the engine in order to control engine torque like we do with a gasoline engine. Instead, there's often no throttle body fitted to a diesel engine, or if it is, it's actually there for a separate reason. It's probably outside of the scope of this webinar. And instead what we do is we control the engine torque by way of fuel delivery. So as I've said, we're always working on the lean side of stoich, and generally we're going to be running very lean air fuel ratios. For example, we may be running somewhere around the region of lambda 10 or even leaner, and probably about the richest we're ever likely to run is maybe 1.1 to 1.2 lambda. So because we've got such a massive range in terms of our lambda based on how much fuel we're injecting into the engine or how much torque or how much power we want, in turn the combustion process, the combustion temperature, also varies dramatically. As we add more fuel, this creates a lot more heat in the combustion chamber. In turn, this is transferred into the exhaust gas temperature, and this is what we're measuring. So we see a much wider range in our exhaust gas temperature in a diesel engine compared to a gasoline engine. And one of the keys, particularly with a modified diesel engine, is one of the the things that we will often end up doing in order to gain additional performance out of the engine is to add more fuel. So more fuel equals more heat in the combustion chamber and more exhaust gas temperature. Again, this is why we tend to monitor the exhaust gas temperature. Just on that note though, in terms of modifying the diesel engine and adding more fuel, generally we are limited in terms of how far we can go with additional fuel by two parameters there. At some point we're going to get to a point where there is insufficient air inside the combustion chamber to provide clean, complete combustion. So this is where we're going to get exhaust smoke, and the other aspect of course is our combustion temperature. Okay, so with that in mind, we obviously need a way of measuring the exhaust gas temperature if this is our most convenient and easiest link back to our combustion chamber temperature. Now, in this instance, because we are measuring very hot temperatures, we might be anywhere in the range of 300 degrees centigrade through to maybe 800-900 or even more. And I will be talking here in degrees centigrade, so I apologize to those of you who are more familiar with imperial units, but of course you can always convert between the two. What we use instead of a typical temperature sensor, which we may be more familiar with for aspects such as intake air temperature and coolant temperature, we use what's referred to as a thermocouple. So I've got one here. This is actually an exhaust gas temperature sensor. So this is essentially what we're going to be using for the task. So it has stainless steel construction, and we have a tip which is actually encased here right at the end of it. This is what we're going to be exposing to the exhaust flow, and what this little tip includes there, which we can't see, inside of that tip we have a joint between two dissimilar materials, and basically what this does is it creates a very small voltage when there's a difference between the temperature that the tip of the thermocouple is exposed to and the other end of the thermocouple. So this creates a very small voltage, and by then amplifying that voltage we can actually make use of it. So the thermocouple on its own is only part of the puzzle. We'll also be running that through a thermocouple amplifier, and then this generally will take that output from the thermocouple itself and generate a 0 to 5 volt output, which we can then feed into an ECU, a data logger, a gauge, a dash, whatever we're actually going to be using for displaying the exhaust gas temperature. So that brings us to the next point of how we are going to use that. So in the case of our test vehicle here, we're running a pre-production or beta version of MoTeC's M1 diesel package. So we've got everything running straight into the MoTeC M1 ECU, and that's how we're going to view that shortly. And this is running through a MoTeC E888 thermocouple amplifier. However, in the majority of cases, we will be actually modifying the calibration in a factory ECU using the technique of reflashing. This makes it a little bit more tricky to get exhaust gas temperature into the factory ECU. It may be impossible. So there are a number of standalone gauges. So these can be placed somewhere on the dash. These are digital or analog depending on who you're purchasing from. And they basically include all of the components I've just mentioned. They include the thermocouple, an amplifier, which may be built into the gauge, and then some way of actually displaying that for you. It is also handy if you can set a visual warning so that if the exhaust gas temperature goes above a point that you're not comfortable with, that you will actually get a visual warning to bring your attention to it. It's very easy if you're driving the truck every day to start becoming a little bit blasé and maybe ignoring excuse me, the exhaust gas temperature sensor. So something that will visually attract your attention when the temperature goes above a certain limit is quite useful. So the next aspect is, once we've got our thermocouple, where are we going to fit it? And this is another area where there's a lot of debate and a lot of confusion. Ideally, what we really want to do is mount the thermocouple before the turbocharger. And I'm going to be talking here about common rail diesel turbo engines. These are the most popular ones for modification, obviously a lot more potential for power. So let me just grab a photo here. If we can just jump across to my laptop screen for the moment. So this is the installation we have on our Toyota Hilux with the 3-litre 4-cylinder 1KD diesel engine. And this is a shot I just took of the exhaust manifold. And we have individual cylinder EGT on this particular application. So here we've got one of our exhaust gas temperature sensors. It's been drilled and tapped into the steam pipe manifold that came with the turbo kit that we're running, and we have in this case cylinder 1 over here on the right hand side, and we've got cylinder 4 over here on the left hand side. So this gives us the benefit of being able to measure individual cylinder exhaust gas temperature. So this allows us for our purposes to do a little bit more data analysis, particularly around individual cylinder fueling, but for most purposes this is complete overkill, and instead what we would want to do is monitor the exhaust gas temperature typically at the inlet to the turbocharger, and this is generally also going to be the hottest position. So this is where we're going to be measuring the exhaust gas temperature, and it means we also need only one exhaust gas temperature sensor. Obviously that cuts down on your complexity and it cuts down on the cost. Now that's the ideal spot because we are measuring the hottest exhaust gas temperature. However, what we find is that in the aftermarket it's actually much more common to fit the exhaust gas temperature sensor post turbocharger in the dump pipe off the back of the turbo. This is easier generally to fit the sensor to. It's easier to drop that section of the exhaust off and physically weld fitting to that section in order to fit the exhaust gas temperature sensor. However, it also is not ideal, and the reason for this is the way the turbocharger works is it is driven by heat as well as exhaust mass flow. So what I mean by this is that if we're measuring the exhaust gas temperature pre and post turbocharger, what we're going to get is a relatively significant drop in temperature across the exhaust wheel of the turbo. So depending on a number of parameters, including the size of the turbo and the current load being placed on the engine, this could vary anywhere from a few hundred degrees centigrade to maybe 100 degrees centigrade. So it's very hard to have a really firm line in the sand as to how we can translate post turbocharger exhaust gas temperatures to what we're really interested in, which is our pre-turbocharger exhaust gas temperature. A lot of people think that the exhaust gas temperature thermocouples are likely to fail, break off and go through the turbocharger. In my own experience from using these on both diesel engines as well as much higher exhaust gas temperature drag racing engines running on gasoline, this simply isn't a concern. The enclosed tip thermocouples are incredibly reliable, and even if they stop actually reading, they're obviously working in a very harsh environment. Even if they actually stop reading, generally that's not going to mean that anything's going to break off and go through your turbocharger. The complexity is that in order to actually fit the sensor pre-turbocharger, it is a lot more work. We can't just drill and tap the exhaust manifold in place. Well, we could, but we certainly shouldn't. That's going to inevitably result in swarf or debris going through the turbine side of the turbocharger, which could potentially damage it. So in order to do this, we do need to remove the turbocharger and exhaust manifold from the engine. It is a lot more work, but that's definitely the recommendation. Okay, so we've talked about how to get that sensor in there and what we are measuring, and we'll now talk about the results of the exhaust gas temperature if that does become excessive. So there's two areas that we're really interested in here, or two areas that we're concerned in. One is damage to the turbocharger. What we find is that the materials that the turbocharger are made out of do have a maximum temperature where they are going to be reliable. This will depend on the particular turbocharger that you're using. OEM turbos generally will fail or become damaged at lower exhaust gas temperatures than some of the specific competition-based turbos that we're seeing from the likes of Garrett as well as Borg-Warner, but anywhere from about 950 degrees centigrade and above, we potentially could start seeing damage to the turbocharger. Turbocharger damage, obviously something we want to avoid, but the more serious issue is that we also can end up damaging the engine internal. So here we're talking about damage to the piston. These can be deformed, melted or cracked, so we want to stay away from that at all costs, and this is why we are monitoring our exhaust gas temperatures. So what we're going to do is go through a few demonstrations here and look at the exhaust gas temperature and see how it will affect our engine operation. After that, we're going to move into some questions and answers. So if you do have any questions that on anything that I've talked about so far during the webinar, please ask those in the comments. Likewise, as we go through these demonstrations, please feel free to add any additional questions. So one of the questions we have, obviously, with this is how much exhaust gas temperature is too much. Now the problem is that in itself is not a particularly easy question to answer, and the reason for this is because the exhaust gas temperature is affected by combustion temperature, but there are also a variety of other parameters that can affect the exhaust gas temperature. So one of these would be, for example, that our fuel injection timing has a big effect on our exhaust gas temperature. So what we see here is that if we advance the timing quite dramatically, what we're doing is we're starting the combustion event earlier in the engine cycle. Generally in a diesel engine, we are injecting the fuel relatively close to TDC on the compression stroke, but if we advance the timing a lot further from that, what we're going to end up with is the combustion process beginning earlier while the piston is still coming up towards top dead center. Now this can easily end up resulting in damage to the piston in terms of melting or cracking, yet by advancing the injection timing, it'll actually show a lower exhaust gas temperature while simultaneously damaging the engine. On the other hand, retarding the timing, what we end up with is our combustion event starting later in the engine cycle. It's going to continue further into the power stroke, and this actually shows a higher exhaust gas temperature. So again, for those who are coming across from the gasoline tuning world, this is quite similar to the effect of our ignition timing on our exhaust gas temperature. Our actual air-fuel ratio isn't changing, but by advancing or retarding the ignition timing in a gasoline engine, this also affects our exhaust gas temperature. Alright, so what we'll do is we'll have a quick demonstration of that effect, and let's head across to my laptop screen for a moment. And what I'm going to do is just get us up and running here on our dyno, and we'll come up to a point where we're at about 2000 RPM, and I'll just explain, while I let everything sort of reach equilibrium, I'll just explain what we're looking at here. So we're currently on our main fuel timing table, so this is the table that we've got sitting here. And at the moment, this is a three-dimensional table. At the moment, we are looking at this particular point that we're operating here, where we've got a fuel mass being delivered of 50 milligrams, and we're running at 2000 RPM. So at the bottom here, we've got our exhaust gas temperature. So this is just the net total or average across all our 4 cylinders. So while I'm talking here, I'm just sort of waiting for this to come up to equilibrium. We're relatively close to that now, so what I want to do is start by advancing the timing. So let's take us from 12 degrees there up to 20. And what we'll see is our exhaust gas temperature, which was just peaking at 403 degrees, we can see that it's actually dropping down. Not dramatic, but we can see that it's dropped from 403 down to about 398 degrees. Okay, so that's one effect. That's the effect of advancing the timing. We actually see a lower exhaust gas temperature. What I'm going to do now is retard the timing. So what I'll do is I'll take it from back down to 12 degrees. We'll see our exhaust gas temperature come back up to 407, 408. Obviously it's still increasing as it reaches equilibrium. Now what I'll do is I'll retard the timing further. So just clarify as well, the numbers in this table refer to the point in the engine cycle relative to top dead center on the compression stroke where the fuel is being injected. So a number of 12 here means that the fuel is being injected 12 crankshaft degrees of rotation prior to top dead center. Okay, so while I've been talking there, we've seen our equilibriums actually come up a little bit. We're sitting at about 418 degrees. So what I'll do now is we'll retard the timing all the way back to TDC. And straight away we can see our exhaust gas temperature shoots up. So we're going up to 430 degrees here. Now it's important to note here that across those 3 tests that we've just looked at, so we've tried 12 degrees, we've tried 20 degrees, and we've tried 0 degrees. We haven't varied the actual mass of fuel being injected. We've just varied the injection timing, or whereabouts in the engine cycle the fuel is being injected, and this results, or this affects the point in the engine cycle where the combustion process is taking place. So we can see that the correlation between our injection timing and our exhaust gas temperature is quite dramatic, and it's really important to keep that in mind. Now, another aspect as well we see in a lot of common rail diesel turbo engines is that the turbochargers fitted to these engines are what's referred to as a VNT, or variable nozzle turbine, VGT, variable geometry turbo. Basically, these are terms that mean that we have a set of vanes in the exhaust housing of the turbocharger that are computer controlled. By opening and closing those vanes, we can affect the amount of restriction that the turbocharger places on the exhaust flow. We can also affect the way the exhaust gas is directed onto the turbine wheel, and affect the amount of energy that is available to drive the turbocharger. But the VNT turbocharger also has the effect of changing our exhaust gas back pressure. So when we do this, when we change our VNT position on our turbocharger, this will also affect our exhaust gas temperature, even though we may not have affected any other parameters in terms of the amount of fuel being delivered, or in fact our air-fuel ratio. So that's another important aspect to consider if you are running a diesel engine that runs a VNT turbo. And the other thing, though, probably one of the most important aspects to consider is the way the fuel pulse width plays a role in our exhaust gas temperature. So as I said earlier, one of the main ways that we will increase the performance of a diesel engine is to supply more fuel. By supplying more fuel, we end up with a larger combustion process occurring. This creates more energy to drive the engine. We get more torque and power, but it also creates more heat. So we'll see exactly how that works. Let's jump across to our laptop screen again. We'll just get back up and running here, and again I'll just explain some of the parameters that we are looking at. Okay, so at the moment up here on the right hand side of our screen we have our fuel delivery table. So this is defining how much fuel we are injecting. I won't get too involved in the complexities of this table. This also, I should mention, carries on a little bit from our diesel engine fundamentals webinar. So if you do want a little bit more information about the way the diesel engine works, that's a great backup for this webinar, so you can check that out for our members in our archive. Okay, so at the moment we are running at 2000 RPM, and while the relevance of this number isn't particularly important, we're basically injecting now 44% of our nominal fuel mass into the engine. Now, this also results in our exhaust lambda, which we can see at the moment being measured at about 1.65 lambda. So again, leaner than our stoichiometric air-fuel ratio of lambda 1. And we are currently sitting at a cruise throttle opening of only 20%. So this is something that we might often be running in this position when we are at cruise. Right down the bottom of our graph here, we have our exhaust gas temperature in purple, and we can see that that's sitting at 459 degrees. Now, at the moment, we haven't got our dyno coming through to you guys at the moment, but at the moment we are sitting at 160 Newton meters of torque. What I'm going to do now is I'm going to increase the fuel mass that's being delivered. So what I want to do is, as I do that, take note of the exhaust gas temperature and watch how that changes. So right now we're up a little bit. We're at about 166, 167 degrees exhaust gas temperature. So what I'm going to do is add 15 to our fuel delivery, 15%. So we've gone from 160 Newton meters to 230, so a significant increase. And we've also seen our exhaust gas temperature jump dramatically. So we've gone from 466 degrees up to 523 degrees, and we're still actually climbing. So quite a significant effect there, just by adjusting our fueling. Actually, I'll also pause that time graph. By adjusting our fueling on both the exhaust gas temperature as well as the torque that the engine is producing. At the same time, if we just look at our time graph here, I'll just enlarge that. And if we look at our lambda here, before I increased the fuel delivery, we were sitting at 1.6 lambda. After I increased the fuel delivery, we dropped from 1.6 to 1.3 lambda. And you can sort of see straight away the trend in our exhaust gas is starting to move up from the point where I increased that fueling. Excuse me. Okay, so we've looked at our injection timing and we've looked at our fuel mass, but it's not just the fuel mass and not just the injection timing that we do need to consider. Diesel engines, particularly common rail diesel engines, modern common rail diesel engines, are incredibly complex, and there is a lot of interaction between the amount of fuel we're delivering and when we're delivering it in the engine cycle. So the fuel mass as well as the injection timing play a part here, and also the other aspect that plays a part is our fuel pressure. So what I want to do here, let's just jump across to my laptop here, and I've got a demonstration here of what we've just looked at with our fuel mass. I should have actually shown you this previously. So this is two points. I do apologize that the text here is probably a little bit difficult to read, a little bit fuzzy, but that's okay. I'm going to explain what's happening here, and I do also thank the guys at MoTeC for letting us make use of this educational material. So what we've got here is two injection pulse widths. So this just backs up the demonstration that we just looked at. So what we've got at the top here is a short injection pulse width, happens to be 0.8 milliseconds. And what we can see is that the fuel is injected, combustion begins, which is the red section here of our little graph. And what we get with diesel engine combustion, we tend to talk about a parameter called 50% burn or 50% heat release, and this is what we sort of look at to deduce exactly how the combustion process is completing. So ideally what we want to do is end up with a 50% burn occurring somewhere relatively close or a little bit after top dead center, so a little bit after the piston has gone past top dead center. Now if we look at that there, that's exactly what we've got occurring. If we look at our second example below this though, this is where we've now increased our injection pulse width from 0.8 milliseconds up to 1.4 milliseconds. So the fuel is injected for longer, and obviously if we're injecting more fuel, it does take longer for that fuel to combust. So what you can see is the effect here is the combustion process lasts longer, and understandably this results in our 50% burn point being retarded later in the engine cycle. So it's taking longer for the combustion process to complete. 50% burn, our half burn or heat release is occurring later in the engine cycle, and this is why we see the exhaust gas temperature increase as a result of this. What we're seeing is the combustion process continuing much later into the engine cycle, and we're seeing the result of this in our exhaust gas temperature. Okay, so the other aspect that we need to consider here, as I was starting to say, is our fuel pressure. So if we're looking at delivering a fixed mass of fuel into the engine, then the fuel pressure that we use to do this can have a dramatic effect on the pulse width that we need to open the injector for. So in other words, if we double the fuel pressure, we can supply the same amount of fuel through the injector with a much shorter pulse width. So this again comes back to the graph that we've just looked at. A longer pulse width means that our combustion process is going to be happening later in the engine cycle, and this increases our exhaust gas temperature. So let's just jump across to our tuning software again, and what we're going to do is I'll just get us back to where we were there. What we're going to do this time is have a look at our fuel pressure. We'll come up to exactly the same point we were operating in first. So I'm going to come up to 2000 RPM, and we're going to come up to, in this case, our table that we're looking at here is our fuel pressure target table. So this is our table of the fuel pressure that the ECU is going to be targeting from our high pressure direct injection fuel pump. So it's the target values here are in megapascals, and right now we're operating with around about 155 megapascals of fuel pressure. So what I'm again doing just while I'm talking here is just allowing our exhaust gas temperature to try and stabilize. We're sitting at around about 407 degrees at the moment. And also what I'm doing here is I'm going to just take note of the torque that the engine is producing. We're seeing 150 Newton meters of torque currently being produced on our mainline dyno. And what we're going to do now is adjust our fuel pressure. We're going to maintain the same fuel mass delivery. So we're not actually going to affect the mass of fuel being delivered. All we're going to do is reduce our fuel pressure, and what this is going to mean is that in order to deliver the same amount of fuel, the injector is going to be open physically longer. Remember, when it's open physically longer, this means the 50% burn point is going to happen later in the engine cycle. So let's just reduce the number in our fuel pressure target table there from 150, 155. We'll drop that down to 100. And at the moment, before I press enter here, we're seeing our exhaust gas temperature sit at about 430, 433 degrees. We'll drop our fuel pressure down. So we've dropped our fuel pressure down, and we can see that now our exhaust gas temperature is increasing. So we're heading through 450 degrees at the moment. Just again look at my dyno, and our engine torque has not been affected, but we have seen the difference there in our fuel pressure increase our exhaust gas temperature. So let's just pause our time graph there, and we'll have a look at that result. Let's just full screen that, and this is the area here where we've changed our fuel pressure. So the two parameters we're looking there are our fuel pressure target and our measured fuel pressure. Prior to making that change, we're sitting at about 150 megapascals. After making that change, we dropped down to 100 megapascals. It's also important at the same time, oh, not that one. If we look here at our exhaust lambda that we're measuring, before making that change, our exhaust lambda is 1.7. Obviously, our exhaust lambda is always moving around slightly. After making that change, our exhaust lambda has dropped very marginally, but we're sitting at about 1.66. So for all intents and purposes, our exhaust lambda has maintained at exactly the same value. And the important point of this demonstration here is this shows that the fuel mass being delivered to the engine has not changed. And then we've of course seen our exhaust gas temperature. Let's just put that in here as a parameter, just so we can see the effect of that. And prior to making that change, we're sitting at 430 degrees, and after making that change, it does obviously take some time to change, so we're sitting at 450 degrees. So you can see there is a lot of intricacy there in the aspects that will affect our exhaust gas temperature, and this is why it's really difficult. Obviously, a lot of people ask, what's a safe exhaust gas temperature to run my engine at? And on face value, that seems like a perfectly sensible question to be asking. But when we actually start delving into it a little bit deeper, hopefully now you can understand that it is actually quite a complex aspect. There's a lot of interactions that are taking place there, and this makes it a little bit more difficult to just have a clear line in the sand of what is a safe exhaust gas temperature to run. So essentially as well, it's important to understand that exhaust gas temperature is a useful metric. It's a useful parameter for us to monitor, but it's also not the be-all and end-all. You need to look at our exhaust gas temperature and consider it in entirety with all the other aspects to the way the engine is running. Now, the other aspect here is when we are getting familiar with a particular engine, you will start building up knowledge with that particular engine, and if you're starting from scratch and you don't have any experience, a good way of starting to see what others are doing is to spend some time on community forums around that particular model, because what you could take from one particular diesel engine doesn't necessarily mean that that safe exhaust gas temperature, which is proven 100% reliable on that application, is going to also be reliable on every diesel engine. So building up some experience or learning from others with your particular diesel engine is a good way to start seeing where the safe limits lie. That being said, I will give you some ballpark guidelines, and hopefully now with everything we've talked about, you'll understand what you can take from this and why they aren't absolutes. But one of the problems with diesel engines, particularly in truck applications, is that the way the truck itself is being used does vary dramatically. And what I mean by this this is obviously a lot of people are buying diesel trucks because they are towing heavy loads, maybe fifth wheel caravans, etc., toy haulers, whatever, a lot of weight behind that truck, and all it takes is a really heavy load like this and a long sustained climb up a hill, and all of a sudden you're creating load on the engine that's essentially impossible to generate if you are running the truck with no load on the back of it. So we need to consider the way the truck is being used. This is particularly important if you are tuning a truck that is being used for towing. A tune that's 100% safe and reliable unloaded could very easily be incredibly dangerous when you've got a heavy load on the truck. So for something that is going to be reliable for sustained high load operation for towing, I would be targeting somewhere in the region of 700 to 750 degrees centigrade as a maximum. We would also allow some variation on this for short bursts of transients, so maybe 750 through to 850 degrees centigrade would be okay for short periods of time, just for transients. So the important thing to understand here, it's not just the absolute temperature, it's also how long that absolute temperature is sustained for. So the longer the temperature is sustained, the more likely the engine is going to end up being damaged. Now, there's also a lot of people using diesel engines, modified diesel engines for tractor pulling and drag racing, where they're heavily modified. Now, obviously these engines are also modified with stronger internal components. Steel pistons, for example, are a really common upgrade, which obviously have a much higher melting point than the cast aluminium that we will see in a production engine, and in those engines sustain temperatures of 900 to 1000 degrees centigrade or even more. May still prove to be very reliable, but of course these engines are built with that in mind and are also probably going to be stripped and rebuilt much more frequently. Last aspect that I want to just cover on here is ways you can reduce your exhaust gas temperature. So if it is too high, what can we actually do about it? So there are a few options here. The first one is some way of leaning out our air-fuel ratio. As we lean out the air-fuel ratio, and we are leaner than stoic, as we lean out the air-fuel ratio, this reduces the exhaust gas temperature and also the combustion temperature. So obviously one way we can do this is to reduce our fuel delivery, but this has the negative effect of reducing our engine power and torque, so probably not something we want to do if we can get away from it. The other way we can lean out our air-fuel ratio is to add more air, and this is why diesel engines and turbochargers are kind of a match made in heaven. By increasing the boost pressure, what we are doing is supplying more air to the combustion chamber, which has the effect, assuming that we are still working within the efficiency range of the turbocharger and it has more headroom in terms of airflow capacity. This has the effect of leaning out our air-fuel ratio. Anything we can do also to reduce our inlet air temperature is going to help there. So an upgraded intercooler, for example, an air intake system to the turbocharger that's going to be drawing in cooler air, all of that is going to help. On the other side of the engine, anything we can do to reduce our exhaust gas back pressure is also going to improve the situation. So freer flowing exhaust systems, larger turbochargers, etc. will all help. All right, we'll move into our questions. At the moment, we've only got one question there from Aidan, who's asked if removing 4 sensors to 1, there will be no implications for the other 3. They can be straight removed and the ECU won't show a fail or go into a limp home and read only number 1, or do you need some sort of block offs for the other lines? Okay, just to reiterate there, the application that we've got is quite unique because we are running an aftermarket ECU, and running 4 individual sensors like that is probably pretty uncommon if you are running an OE factory ECU that you're reflashing. So in this case, the way the MoTeC ECU works is that it can monitor all 4 EGT sensors together, and then the parameter that we were looking at during our demonstration is the average of those 4. If one of the sensors is removed or is deemed faulty by the ECU, then it's taken out of that equation, so it's not going to cause a limp home mode or a fault code. But if you are obviously going to remove those sensors, you're going to also need to block those holes in the exhaust manifold.
That was just a taste of what we put on every week for our HPA Gold members. Our Gold members are able to watch these live and ask questions and get answers while we're presenting. After the webinars have been hosted live, they're added into our webinar archive where our Gold members can rewatch them at their leisure. We've currently got over 240 hours of existing webinar content covering topics on engine building, engine tuning and wiring. This is one of the fastest ways to expand your knowledge on a wide range of topics, as well as to stay up to date with the latest tools, trends and techniques in the performance industry. Our Gold members also get access to our private members-only forum, which is the best place to get fast answers to your specific questions. Gold membership can be purchased for just $19 per month. However, you'll also receive 3 months of free access with the purchase of any of our courses. Click the link in the description to learn more.